In the previous lecture, we have talked about the solution of a Legendre equation which is of the form 1 minus x square y double dash minus 2x y dash plus n into n plus 1 y equal to 0. About its ordinary point x is equal to 0, we got the solution. It is of the form y equal to a0 into 1 minus n into n plus 1 by 2 factorial x square n into n minus 2 n plus 1 n plus 3 upon 4 factorial x power 4 minus so on plus a1 into x minus n minus 1 into n plus 2 upon 3 factorial x cube plus n minus 1 into n minus 3 into n plus 2 into n plus 4 upon 5 factorial x power 5 minus so on. And we have note that if this n is an positive integer, then any one of them, this series will be 0, and that is known as a Legendre polynomials. We also talked the solution of Legendre equation about its regular singular point x is equal to 1, and which we got into the previous lecture is in the form of hypergeometric equation, which is the solution is of the form y is equal to f of c1 into f of minus n into n plus 1 1 minus x by 2 plus c2 into the same thing y f of minus n into n plus 1 1 minus x by 2, this multiply by b0 log of 1 minus x by 2 plus b1 1 minus x by 2 plus b2 by 2 1 minus x by 2 whole square and so on. So this was the things which we have discussed in the previous lecture. Now in this lecture we will discuss some related properties of this Legendre polynomial, and we will see that what are the properties of this Legendre polynomial. So what will be this quantity if your n is an integer here that we have considered also in this case. So these are the two solutions we got in the previous lecture about x is equal to 0 and x is equal to 1. So now let us discuss a definition of Legendre polynomial, or I can say nth Legendre polynomial. The polynomial of a solution of polynomial solution of Legendre's equation is the nth Legendre's polynomial. So what is the solution? Whatever the solution we got as a equation of the Legendre polynomial, it's called the Legendre polynomial, and it is denoted by Pn of x is equal to f of minus n, n plus 1, 1, 1 minus x by 2. So if you expand this by geometric series expansion or hypergeometric series expansion to this, as we know that, let us write down what is this f of a, b, c and x will be represent. It will represent 1 plus summation n running from 1 to infinity a into a plus 1 up to a plus a minus n plus 1, b into b plus 1 up to b minus n plus 1 by n factorial into c plus 1, c plus 2 up to c minus n plus 1 into x raised to n. This is the Gauss hypergeometric series we have. So according to this, we will use that things here. This Pn of x we can write as Pn of x is equal to, which is we have f of minus n, n plus 1, 1, 1 minus x by 2. So as per that which we have here, it is 1 plus summation a into a plus n up to a minus n plus n. So the first term we have, it is minus n into n plus 1 by n factorial into 1. This is your a, this is your b, and this value is your c. That is a, b, and c. And into x, 1 minus x by 2. Instead of x, we have 1 minus x by 2. The second term is minus n, then minus n plus 1. For the term b, we have n plus 1, n plus 2 upon 2 factorial into c plus 1. C is 1. So that is 1 into 2. And into 1 minus x by 2 whole square. That is x square. The third term will have minus n plus 1, minus n plus 2. Then it is n plus 1, n plus 2, n plus 3 upon 3 factorial into 1 into 2 into 3. That is actually c into c plus 1, c plus 2. C is 1 into 1 minus x by 2 whole cube up to so on. The last term you will have, it is minus n plus 1 up to so on minus n plus n minus 1, n plus 1, n plus 2 up to so on n plus n upon n factorial 1 into 3 into up to n into 1 minus x by 2 raised to n. What will be the next term? Because this summation is running from 1 to infinity. So here I have written the term which we having the nth term. What will be the next term? When you will have here, then it is the term n plus 1 is there, and n plus 1 will cancel with this, because of if your a value of a is n minus 1, then this n will get cancelled out, 1 is also get cancelled. So that means you will have the term until this, and all the rest of the term will become 0. So that is a polynomial in terms of x. And this can be simplified as, if I take this minus sign, if I multiply that sign here, okay, then this quantity can be simplified and rewrite as 1 plus n into n plus 1 by 2 upon 1 factorial square into 2 into x minus 1. So you just take this minus sign, this minus n, you just multiply here, then it is x minus 1 is there. So in the second term, again, what you will do, this minus and this minus minus become plus. And this 2 and this 1 into 2 is a 2 factorial square. So that we can write down plus n into n minus 1, n plus 1, n plus 2 upon 2 factorial square into 2 square into x minus 1 square. Because it is a square, there is no need to change the sign. In the third term, there is 3 minus sign is come out of this, where minus minus will become plus, and one sign you will change here. So that will gives you n into n minus 1, n minus 2, n plus 1, n plus 2, n plus 3 upon 3 factorial square into 2 raised to 3 into x minus 1 whole cube up to so on. And the rest, that is the last term you will have, which again you can adjust. This is 1, so you will have it is n into n minus 1 up to 1. That is n plus 1, n plus 2 up to 2n upon n factorial square into 2 power n into x minus 1 power n. So this is the equation 1 is your Legendre polynomial is there. Now this is in the coefficient of, or it is in powers of x minus 1 raised to n. And one can note that what will be the coefficient is here. If you can simplify this quantity, then you may just note down that this is 1 into 2 into 3 up to n. This is 2n plus 1, n plus 2 up to 2n. So this is actually 2n factorial upon n factorial square into 2 power n. That is the coefficient of x minus 1 raised to n that we got from this quantity. So that we can write down note as a note. Note that the coefficient of x minus 1 raised to n is 2n factorial upon n factorial square into 2 power n, which we exactly got it from here. Now it is for n is running from 0, 1, 2 up to so on. Also, one more remark we need to write down here, because in the previously what we have got into this solution, either this term will be 0 or this term will be 0, and it says that either it will have even terms or it will have odd terms in it. So Legendre polynomial is either contains the even powers of x or it will contains the odd power of x. So that we can write down as a note here. Note that the Legendre polynomial is the solution of Legendre equation, and it include either only even power of x or only odd power of x. Pn of x can be written as this way: Pn of x is equal to an x raised to n, an minus 2 x raised to n minus 2, an minus 4 x raised to n minus 4, up to so on. It will be last time is a0 if it is an even power, or it will be a1 into x. Any one of them can be possible. So this Legendre polynomial is always having the coefficient of the even power of x or odd power of x is there. Now let us discuss some properties of Legendre polynomials. As we have discussed the properties of Chebyshev polynomial, into the similar manner we have polynomial property of Legendre polynomial. The first property says that prove that Pn of 1 is equal to 1 and Pn of minus 1 will be minus 1 raised to n. So let us discuss the solution for this. From the previous slides, that means from this is our Pn of x that we have concluded. So what will be the P1? That means if I replace x is equal to 1 in this quantity will become 0. This will become 0. This is also will become 0. This is also will become 0. So only one term is you will get, which is 1. So hence, from equation 1, we get Pn of 1 equal to 1. Inside what we can say is taking x is equal to 1 in equation 1. If you substitute x is equal to 1 in the equation 1, you will definitely get P1 of 1 is 1. Now let x is equal to minus 1. In the equation this, which we have obtained, I will call it this is equation 2. So in the equation 2, then P of minus 1 will be an power minus 1 raised to n plus an minus 2 minus 1 raised to n minus 2 an minus 4 minus 1 raised to n minus 4 up to so on. Now there will be two cases: either this n is an even number or it is an odd number. Suppose what happens if n is an even, then what is P n of minus 1? If it is even, then it is minus 1 raised to n, which is an even number. So it is, this value is 1, this value is also 1 because it is an even power of minus 1. So it will have an plus an minus 2 plus an minus 4 up to a0 you will have. Now what is this? This is exactly the Pn of 1 into that. If you substitute x is equal to 1 into previous one, this is Pn of 1. But Pn of 1, we have already proved that it is 1. So that's why this is 1. Next, if n is an odd number. So if n is an odd, then what is Pn of minus 1? As per the definition of Pn of x, which we have from equation 2, you substitute, instead of x, you substitute n equal to minus 1 here. So you will get an into minus 1 raised to n, an minus 2 minus 1 raised to n minus 2, an minus 4 minus 1 raised to n minus 4, up to so on. A1 x is there. Sorry, not x, but minus 1. So what will be this gives? This will gives you minus an, because n is an odd number. So n minus 2 is also odd. This is minus an minus 2. This will be minus an minus 4 up to so on minus a1. If you take minus common, you will have an plus an minus 2 up to so on an. And this is exactly p of 1. So that's why it is minus 1. So hence, Pn of minus 1 is either 1 or minus 1, which will be depends on n, whether n is even number or it is an odd number. So I can say if it is 1, if n is an even, minus 1 if n is odd, which I can write down in mathematical terminology, it is minus 1 raised to n, or any n union singleton 0. Now we have a next result, which known as the Rodrigues formula. Okay. So this result is says that state and prove the Rodrigues formula for Legendre polynomial. So what is the logic? This formula, it is says that, or not sorry, prove that Pn of x is minus 1 upon 2 raised to n into n factorial, nth derivative of x raised to x square minus 1 power n. This is the Rodrigues formula, which where this Pn of x is the Legendre polynomial. So what we can note here is Pn of x, we already calculated what is Pn of x. We note that the nth Legendre's polynomial is Pn of x is equal to f of minus n plus 1, 1, 1 minus x by 2. This is the value of this Legendre polynomial is there. If we can expand this one, then we can write this is 1 plus, as we have did it earlier, that we have did it here. Okay, the same thing we need to do it here. So I can just copy that quantity here, that is n into n plus 1 by 2, or I can say 1 factorial square into 2 into x minus 1 plus n into n minus 1, n plus 1 into n plus 2 upon 2 factorial square into 2 raised to 2, x minus 1 raised to square, up to so on. The last term is 2n factorial upon n factorial square into 2 power n into x minus 1 raised to n. If I call it, this is as equation 1. Now we know that this Pn contains either even powers of x or only odd powers of x. So now also we know that this Pn of x contains either only even power of x or only odd power of x. So we can write Pn of x is equal to an x raised to n, an minus 2 x raised to n minus 2, an minus 4 x raised to n minus 4, up to so on. And we call it, this is as equation 2. And if you compare this previous step, and we know that the coefficient of x raised to n, or I can say nth term, see, first of all, these two things are not comparable because this is in powers of x, this will be in powers of x minus 1. But the coefficient of x raised to n I can able to write down in general. So from equation 1, it is clear that the an is 2n factorial upon n factorial square into 2 power n. This is our an. And we got the recurrence formula for Legendre polynomials. So that recurrence formula we have to write down using that for series solution for x is equal to 1. That will be here. This is the recurrence formula which we have derived earlier. That is ak is minus of this quantity. So using this recurrence formula, we can able to write down, or we can able to derive. So let us write down the recurrence formula is ak equal to minus of n minus k plus 2 into n plus k minus 1 by k into k minus or I can just take out this ak into this quantity on the other side. So that is ak into ak minus 1 upon n minus k plus 2 n plus k minus 1 into ak. If I call this is as equation 3. Now what our objective? Our objective is to write down this an minus 2, an minus 4, an minus 6, all of them in terms of ak. That is our objective. So we'll write, we want to write an minus 2, an minus 4 up to so on in terms of an. So we shall take k equal to n, n minus 2, n minus 4, and so on in this equation 3. So if I replace this instead of n minus 2, then for k equal to n, we will have an minus 2, which will be gives you, if instead of n we can replace n, so instead of k we can replace n, so it is n into n minus 1 minus n into n minus 1 upon, in the denominator we'll have 2 into 2n minus 1, because instead of k we have to replace n. If you replace n, this will be gives you 2 and this will be gives you 2n minus 1, and this is an. For k equal to n minus 2, we have n minus 4, which is minus n minus 2 into n minus 3 upon 4 into 2n minus 3 into an minus 2. But an minus 2 is already we have calculated here. So that's why we can write down this is as minus minus become plus n into n minus 1, n minus 2, n minus 3 upon 2 into 4 into 2n minus 1, 2n minus 3 into an. Similar manner, if I have k equal to 4, n minus 4, then we'll have an minus 6. As per this, and if you can substitute this n minus 4 value into that, we will have that is minus of n into n minus 1, n minus 2, n minus 3, n minus 4, and n minus 5 upon 2 into 4 into 6 into 2n minus 1, 2n minus 3, 2n minus 5 into an, and so on. You will have further these terms, and we'll substitute all these values of an minus 2, an minus 4, an minus 6 into the equation 2. What was equation 2? Let us see that. So this was the equation 2. We substitute all this value of an minus 2, an minus 4, all this value, and an is this. Okay, an we already calculated this. N minus 2 we also have. Let us write down first of all, we substitute all these values of an minus 2, n minus 2 there, and then we'll substitute that value of an. So substitute to equation 2, we get Pn of x. You note that this an is common out in each and every term, so that's why I take it common. Then you will have x power n minus, this is the first term, an minus 2, that is minus of n into n minus 1 upon 2 into 2n minus 1 into x raised to n minus 2. The next term is plus n into n minus 1, n minus 2, n minus 3 upon 2 into 4, 2n minus 1, 2n minus 3 into x power n minus 4. Then you will have further terms. In general, kth term can be written as minus 1 raised to k n into n minus 1, n minus 2 up to n minus. So when it is n minus 2, it will be 2 term. It is 4, it is a third term. When it was a 6, then it goes up to 5. So if it is x power n minus 2k is there, then it goes up to 2k plus 1 upon 2 into 6, sorry, 2 into 4 into 6 up to so on 2k. Then it is 2n minus 1, 2n minus 3 up to so on 2n minus 2k plus 1 plus so on. If I call this is as equation number 4, and I also replace this value of an, where the an we already have 2n factorial upon 2 power n into n factorial square. This is the value of an that we can replace here. Now let us compare or consider the coefficient of x raised to n minus 2k, and let us observe what is this quantity is. Now let us consider the coefficient of x power n minus 2k. The coefficient of x power n minus 2k is minus 1 raised to k, which we have calculated n into n minus 1 up to n minus 2k plus 1 upon 2 into 4 into 6 up to 2k into 2n minus 1, 2n minus 3 up to 2n minus 2k plus 1. Now, so this is the things we have. What is the numerator? Let us see what is the numerator here. So now, if I call it this expression as a fifth expression, now the numerator of 5 is, what is the numerator? It is minus 1 raised to k n into n minus 1 up to n minus 2k plus 1, which I may write down as minus 1 raised to k n into n minus 1 up to so on n minus 2k plus 1. What will be the next step? I'm just adding and subtracting n minus 2k factorial here upon n minus 2k factorial. So multiplying and divide n minus 2k factorial. Since if you multiply and divide by n minus 2k factorial, this is minus 1 raised to n into n factorial upon n minus 2k factorial will have. We call it this is as a sixth expression. Now let us look at the denominator of this fifth expression. So now consider the denominator of the fifth expression. What is the denominator? Is 2 into 4 into 6 up to 2k into 2n minus 1, 2n minus 3 up to 2n minus 2k plus 1. Now, if I common out 2 from each and every term from this, then what will we have? If I, how many times this 2 is common? 2 power k will be there. Because 1 2 is common from this 2, another 2 is common from this 4, then from this 2. So what is left? It is 1 into 2 into 3 into up to k is left. If I common out 2 from each and every quantity here. So it is 2 power k into actually k factorial will have. And for this, I may multiply and divide some quantity. So 2n is multiply and 2n is divide. And 2n minus 1 is already there. 2n minus 2 I multiply and 2n minus 2 I'll divide. Then similarly 2n minus 3 multiply and 2n minus 3 as it is, and 2n minus 4 multiply and divide up to so on. The last term is 2n minus 2k plus 1. And lastly, what is the next term we multiply is 2n minus 2k factorial I multiply. That will be the next term, and we'll multiply up to so on. The last term is 2n minus 2k plus 2 and 2n minus 2k factorial I'll multiply and divide. So if you can do this, then what is this quantity which we have here? This is actually the 2n factorial. This is k factorial. And you just observe, if you common out 2 from each and every quantity from this denominator, then it is 2 power k. What is left? Let us write down. That is 2 power k into k factorial, and this is 2n factorial in the denominator now. If I common out 2 from each and every quantity here, then it is how many times 2 is common out? How many terms are here? Altogether, there are up to here, there are k terms up to here. I'm not including this 2n minus 2k, I'm not writing, but to this term will have k term. So it is 2 power k is common out. What is left inside it is n minus 1, n minus 2 up to so on, n minus k plus 1, and we multiply and divide by n minus k factorial, and into this 2n minus 2k factorial we multiply and divide that. We already there, sorry. So finally what we get from this 2 power k is cancelled out. So we'll have k factorial into 2n factorial, n minus k factorial upon. Now what is this? It is n into n minus 1, n minus 2 up to n. This if you go further up to 1. So it is actually n factorial into 2n minus 2k factorial is there. And we call it, this is as expression 7. Now putting this value of this 6 and 7 in 5. So we can write substituting the value of 6 and 7 to 5, we get the coefficient of x power n minus 2k, because that was the coefficient of x power 2k, x power n minus 2k. That is this. So numerator is this, minus 1 raised to n factorial equal to minus 1 raised to k into n factorial upon n minus 2k factorial into this quantity, but this quantity is in the denominator. So the reciprocal of that we will write that. That is n factorial into 2n minus 2k factorial upon k factorial into 2n factorial into n minus k factorial. So now what we can get? So from equation 4, we note that, what was the equation 4? Let us see that. In this, what will happen? Whenever this n minus 2k is greater than or equal to 0, that means n is greater than or equal to 2k, which I can equivalently write down n minus 2 is greater than or equal to k, which I can write down k is less than or equal to n minus 2. All these statements are same. So that we can write down there. We note that n minus 2k is greater than or equal to 0 if and only if n is greater than or equal to 2k, if and only if n minus 2 is greater than or equal to k, if and only if k is less than or equal to n minus 2. This I need actually to write down this expression 4 in terms of summation form, because this coefficient we calculated and into an is there. So an is this. First I will write down this an. So it will be Pn of x is equal to an. An is 2n factorial upon 2 power n into n factorial square. Summation k running from 0 to box n by 2. That is exactly the same thing which we have here. K is less than or equal to n by 2. We got from this. Then it is an x raised to n minus 2k. This is the coefficient of x raised to n minus k. So we'll write this coefficient here. That is minus 1 raised to n into n factorial. This n factorial and this n factorial become n factorial square. 2n minus 2k factorial upon n minus 2k factorial into 2n factorial into n minus k factorial into x power n minus 2k. You just observe this n factorial will get cancelled and this 2n factorial is also get cancelled. So finally what we have, it is 1 upon 2n factorial k running from 0 to box n minus 2 minus 1 raised to n into 2n minus 2k factorial upon k factorial. Oh, this k factorial is I have left. No, that I forgot. So here k factorial is also there. K factorial, then it is n minus k factorial, n minus 2k factorial is there. and this 2 raised to n is already written, into x power n minus 2k we will have. We call it this is expression 8. So Pn is equal to this. What is our objective? Is to prove that the Pn is of the form this 1 upon 2 raised to n n factorial nth derivative of x square minus 1 raised to n. So now we will see what is the nth derivative of this x raised to n x square minus 1 raised to n. So for that we need to remember, or we need to recall one formula. What is the nth derivative, or recall that? What is the first derivative of x raised to n? That is m into x raised to m minus 1. Second derivative, or in general nth derivative, we can also able to write down. So nth derivative will be m into m minus 1 up to so on m minus n plus 1 into x power m minus n. This quantity I can rewrite as m into m minus 1 up to so on m minus n plus 1 into m minus n up to 1. I multiply m minus 1, m minus n plus minus 1 and so on up to 1, multiply and divide. Into x power m minus n is already there. So this is what? This is m factorial upon m minus n factorial into x power m minus n. So using this, if I want to write down what will be the nth derivative of x power 2n minus 2k. So as per this, instead of m we have this. So it is 2m minus 2k factorial upon 2n minus 2k minus n factorial into x power 2m minus 2k minus n. So that can be rewrite as 2n minus 2k factorial upon n minus 2k factorial into x power n minus 2k. This will be the expression we got. So from this, what we can observe is this quantity is we have here, which we have derived here. This is exactly n minus 1 2k. So instead of, so from 8, from equation 8, we get Pn of x equal to 1 upon 2 power n into n factorial summation n k running from 0 to box n by 2 minus 1 raised to k into n factorial upon k factorial into n minus k factorial into d by dx raised to n into x power 2n minus 2k. So you can just see that is exactly the things we got. minus 1 raised to n k factorial into n minus k factorial. And this quantity which I have drawn with the green color, it is exactly we have derived here. So we have substituted that value over there. So this expression we can get. But ultimately our goal is to prove this is the nth derivative of 1 x raised to square minus 1, x square minus 1. That is our objective. Now this summation is actually from 0 to n minus 2. Our goal is to extend this is from 0 to n. So now we extend this summation from k equal to 0 to n. As for k is greater than n minus n by 2, this will implies 2k is greater than n. This will implies n is less than 2k, and which will implies n minus 2k is less than 0. And this 2n minus 2k is always less than n. This will give you, if I add n both sides, this will give you this. So this 2n minus 2k is always less than n. So if I take the nth derivative of x raised to 2n minus 2k, it will be 0 if your k is greater than n by 2 due to this quantity. Okay, for example, if you have the x power 5, if you take the derivative of x raised to 5 6 times, then it will become 0. So if this value is bigger than its derivative, smaller than its derivative, then it is always 0. So here exactly the same quantity we are getting. This 2n minus 2k, if it is less than n, that means k is greater than n by 2, then this derivative will become 0. So what will be the n plus 1 if I adding this? So all the derivative instead of n by 2 here, if I add anything over there, all the 0 term we are adding into that. That means I can write down this summation from 0 to n now. Instead of n by 2, we can write down 0 to n. Because we are adding 0 term. Because this derivative is 0, so we are adding 0 term into that. So that's why this will be Pn of x will be 1 upon 2 power n into n factorial, summation k running from 0 to n minus 1 raised to k into n factorial upon k factorial into n minus k factorial into d raised to n upon dx raised to n into x power 2n minus 2k. Now if I take this derivative outside to this, so this I can rewrite as 1 over 2 power n into n factorial d power n raised to x raised to n. That means this, which is summation k running from 0 to n. This quantity that we have here is exactly the nck, and x power n minus k is there into minus 1 raised to k, which we have written here. So this green quantity is nck. This derivative I have taken out of this summation and just rewriting this quantity. Now, can somebody tell me what is this quantity? If you can just see the binomial expansion of x square minus 1 power n. X square minus 1 power n, the binomial expansion of this by a plus b power n. The binomial expansion of this one is k running from 0 to n, nck, a raised to n or a raised to k, b raised to n minus k is there. This is the binomial expansion. So using this, if you can write down this was k running from 0 to n, nck, instead of this is b if I write down, that is minus 1, this is minus 1 raised to k into x square raised to n minus k, that is x square raised to n minus k. So this actually, this expression summation of this quantity is exactly x square minus 1 power n. So this is 2 power n into n factorial, nth derivative of this into x square minus 1 power n. This is the quantity is required, and the binomial, using the binomial theorem, we can got this. So this proves that our objective of to obtain the Rodrigues formula for Legendre polynomials. If you have any doubt, you can ask for to proving this statement.
સર જે nth legendre polynomial હતી ને એમાં જે લાસ્ટ સ્ટેપ છે ને એમાં તમે જે વેલ્યુ મૂકી છે ને -n n+1 1 -x/2 એમાં લાસ્ટમાં b ની વેલ્યુમાં 2n કઈ રીતે આવે?
બાકી એકનું પીવાય નું આપો તમે 1:30 વાગ્યાથી લઈ લો તો વાંધો ના આવે.
ચાલે છે ઉપર ખબર નહીં બંધ થવું.
મારે બેનો દીવા લાગ્યો કે નીકળી જવું તો આ સફળ જતા રહેશે.